Welcome to this module 4 of digital image processing. Module 4 mainly deals with chromaticity and all the image restoration and techniques. So let's start. First is what is chromaticity. So chromaticity, if you see like in basic English, if you define the chromaticity is a way of describing the color of light, okay, and separate from how bright the light is. So what happens here is like if I check for the basic definition as per textbook, it is the property of color that mainly describes the quality, that is the quality of the color and the characteristics which distinct it from its luminescence. That means from this luminescence power, how you can differentiate it is known as chromaticity. And also how chromaticity is useful, it is mainly help us to check how light and dark a particular light appears. Okay, next is characteristics. What are the characteristics of chromaticity? First is brightness. So what is brightness? Brightness is nothing but the intensity or the quality of the color. Fine. Next is indicates how much light is emitted or reflected from an object. For example, if I have an object, so how much light is emitted or reflected is all about brightness. Next we have is hue. So hue is nothing but it represents the dominant wavelength in a mixture of wavelengths. Okay. So in a mixture of wavelengths, the particular wavelength which is dominating throughout is also known as hue, and also it describes the color which is perceived. Next we have a saturation. What is saturation? Saturation refers to the purity of the color, how pure the color is, and also pure spectrum color. If you see, that is the color is mainly represented in the form of a spectrum. So if you consider all the pure spectrum colors, they are all considered fully saturated, while the colors which are mixed are considered very much less saturated. Okay, so if you combine both hue and saturation, uh, adding both of them, you get the chromaticity. Okay, next we have a tri-stimulus values and trichromatic coefficients. Tri-stimulus values are mainly the colors which can be represented by the amount of RGB component present. Okay, that is red, green, and blue. You get to reproduce it. So how you are representing it is mainly represented by capital X, capital Y, capital Z. These are nothing but the tri-stimulus values, whereas the trichromatic coefficients are mainly determined by small x, small y, small z. So what are the equations for that? Small x is equal to capital X upon divided by capital X plus capital Y plus capital Z. That means for trichromatic coefficient for red color, it's mainly given by the tri-stimulus color of red divided by that of R plus G plus B, same as that of Y also and Z also you calculate. Fine. Next is the CIE chromaticity diagram. This is very much important when it comes about exams. So the figure looks like this. You have to remember it forms a particular shade. I'll change the color of this pen. Okay, so you see this part is supposed to become red. This is again some bluish kind of thing. Here again it is green. In between you see some yellow color. Here you get a white color. Okay, so this is nothing but a CI chromaticity diagram. You have to draw the diagram like this. This is your x-axis and this is on the one is a y-axis. So graphical representation of a color composition is mainly based on the red and the green color coefficients. So if you want to calculate the z value, that is x plus y plus z is equal to 1. So if any two components automatically the third component you can derive it by simply substituting the values. Correct? X plus y plus z equal to 1. So that is z equal to 1 minus bracket you take x plus y. Okay. So edges of the diagram. So whatever the edges you have, this particular edges of this particular diagram, so they all represent the pure spectrum of colors. Your pure spectrum of colors mainly deals with the colors like violet as well as red. The violet, the wavelength is 380 nanometer, for red it's 780 nanometer, and rest the interior points represent the spectrum of colors, because obviously it is interior of the figure, so a different spectrum of colors can be obtained. And also there is something known as points of equal energy. What is points of equal energy? Corresponds to the equal contribution of red, green and blue. So if there is an equal proportion of red, green and blue color representing the standard white light, then it's known as point of equal energy, and also these colors are very much less saturated. Okay, next is the RGB color model. The RGB color model is mainly represented by this diagram. You can see, okay, this part is magenta, this part is blue, this part is cyan, this part is white, this vertices is red, this vertex point is black, this is yellow, and this is green. Accordingly you put all the coordinate values. This you already know, I guess, from your 3D geometry and everything. So RGB color model is a fundamental framework. Okay, important word, framework for representing the colors in a digital system, and also it is mainly used where you are using it. It's mainly used in the field of computer graphics, image processing, as well as display technologies. So RGB color composition, the primary components the name says is RGB. So R is red, green, and blue. Okay, so overall you have 256 colors, but some of the systems may support only 216 colors only. So this property where some systems support only 216 colors but not 256 colors is also known as safe color. That means only this much, only these many colors and only system can only show. Others it won't show. It will be only. Okay. What is the Cartesian space? How you're representing it? It's a 3D Cartesian system where x, y, z axis is there. X, y, and z. Now, what is a gray space lining? A gray space lining is not a gray space line. What is a gray space? And you can see one. This line is nothing known as the gray space line. So this gray space line is nothing but a line which is connecting from black to white and represent the grayscale levels where all the three components, that is your R, G, and B, are equal. Okay, next is pixel depth. What is a pixel depth? The name says depth of a pixel is mainly determined by the number of bits used to store the RGB value. That means number of bits where you use to store the RGB value is nothing known as the pixel depth. Next we have is the 8-bit per channel. What is 8-bit per channel? It is mainly results in a 24-bit depth for each pixel. So it allows these many colors. Next is full image color. Full image color is mainly referred to 24-bit RGB images. Pure red, white, and black is mainly represented by the hexadecimal format FF4 zeros. White will be all 6 times F and black will be all 000 zeros. So if when it comes about RGB color model, you have to write this whole explanation, okay, along with this diagram. Next is CMY and CMYK model. What is CMY model? It mainly stands for cyan, magenta, and yellow. Okay, primary pigment colors. And the SCMY model is also known for its subtractive nature. What is subtractive nature? For example, cyan light is mainly obtained when you subtract the red light. The magenta color is mainly obtained when you subtract the green light. The yellow color is obtained once you subtract the blue light. Fine. And what is one of the speciality of this cyan color is cyan color will absorb the red light from the white light, reflecting green and blue. So cyan light can also, you can say, will absorb all the red light, and once it absorbs the red light, it will reflect back the green and the blue light. So what are the conversion techniques RGB to CMY? So in order to convert an RGB model to a CMY model, you perform some normalization techniques. Normalization techniques will mainly range in the value of 0 to 1. So C is equal to will be 1 minus R, M is equal to 1 minus G, Y is equal to 1 minus B. So similar to C, M, Y, R, G, B. Peace. Next is CMYK model. What is CMYK model? That is combination of equal parts of cyan, magenta, and yellow should yield a black color. Okay. Now, sometimes what happens is when you try to make this combination, it will produce a very muddy and a dark gray color. Why it is produced? It's mainly produced due to the imperfect pigments in the printing process. Sometimes what happens is when you try to mix some of the colors, it won't give you as such a good texture. It will provide you a very muddy and dark gray like appearance. So it mainly occurs when you try to mix up cyan, magenta, and yellow in equal proportion. So in order to produce a proper color in the sense it should be either in a deep or a true black color. A fourth color you are adding into the system, that is K. K is nothing known as black only. Okay, so it is mainly using graphic cards. So CMY, if I consider this matrix, is equal to 1 1 1 identity matrix is equal to minus RGB. Next is your HSI model. The HSI model mainly describes how humans perceive the color on the basis of hue, saturation, as well as intensity. So based on intensity, saturation, and hue, how you are trying to describe a HSI model. So what is hue first? Hue mainly represents the type of the color, what type of color you are using, and also defines the angle of color vector in a plane perpendicular to the intensity axis. Okay, next is typically the red axis is mainly 0 degree, and hue indicates it mainly increases counterclockwise. So when you're trying to increase the angle, it mainly increases counterclockwise. So 0 is for red, 120 is for green, 240 is for blue. Next is saturation. What is saturation? Saturation mainly determines the purity of the color. Okay, purity of the color, it mainly calculates the intensity from the vertical intensity axis. So from the vertical intensity axis, we're calculating the saturation, and also colors closer to the axis. So which are closer to the axis are very much less saturated. They're represented between the values of 0 and 1. So saturation for S equal to 0, it appears completely desaturated and gray in color, whereas S equal to 1 is fully saturated and pure in color. Next is intensity. Intensity, nothing that refers to the brightness or the grayscale value of the color. Okay, and it is mainly determined by the position along the vertical axis from black to white. So intensity is also determined by the vertical intensity axis only from the black to white, whereas the saturation is all about you can say, yes, only from the vertical intensity axis, not from any particular color. So I equal to 0, I equal to 1. For I equal to 0, it's a black and no light. For I equal to 1 is a white maximum light. So these are the formulas. The same thing again is described here. If I consider this a particular my prism, okay, this portion is green, this is cyan, this is black, this entire part is red, this is white and yellow. So R and S. So mainly theta is nothing but cos inverse of half of R minus G plus R minus B divided by R minus G whole square plus R minus B into G minus B square root. Okay, so how it is coming along is not required, only remember the formulas, that's it. So how you calculate saturation component? Saturation component is mainly given by S equal to 1 minus 3 upon 3 is nothing but the 3 components which you are using, R plus G plus B, I equal to a half 1 by 3 of RGB. Okay, so converting, how will you convert an HSI to RGB? So B is defined by B is equal to I into 1 minus S, R equals to I into 1 plus S cos H upon cos 60 degree minus H, G is equal to 3I minus R plus B, and H is equal to 1, H is equal to H minus 120. This is given. Now once you're trying to convert the same, now again what happens is the equation becomes ulta. So R equal to I into 1 minus S, again G will become I into 1 plus S cos H upon 60 degree cos 60 degree minus H, and B is equal to 3I minus R plus G. These three formulas, you have to remember it. Next is intensity slicing. The name says slicing, cut off something. That is, it is mainly used in pseudo color processing, with the intensity levels of grayscale image. Whatever grayscale images you are having are mainly divided into smaller intervals or distinct colors is mainly assigned to them at a particular level. Okay, like if I consider this as a particular image and then I have this as my slicing plane, I'll just apply this and will just slice it off into two equal regions. Okay, then so what is a slicing plane? Slicing plane, planes which are parallel to the xy axis and are placed at various intensity levels. Yes, it is an xy axis only. Now since this is a particular image, each an image, the particular pixels are distributed randomly throughout and everyone is having different intensity. Correct. So once you try to slice it off, it will slice at different functions into regions. Then is color assignment. How you're assigning the colors? Colors are mainly assigned to the intervals between the slicing planes. So pixels are all color coded. That means based on which the intensity levels falls into. Now mapping. How will you try to map it? Now grayscale mainly ranges from value of 0 to L minus 1, where L is nothing but the intensity levels. Planes are divided at intent. Now once you are done with this, now again planes will be there where you will try to uh, divide it off. So L1, L2 and L3 is mainly used to partition the range into P plus 1 interval. That means in P plus 1 intervals, again L1, L2 and L3 represents different intensity levels. So specific color, how will you assign it to a particular interval? So it's mainly given by f of x comma y is equal to c1 c2 up to c of p plus 1. P plus 1 is nothing but at a particular plane. Okay, so it is this given by this formula, f of x comma y should be less than L1, L1 less than equal to f of x plus y less than L2, and f of x comma y greater than equal to L of p. So where it is mainly used to intensity slicing, first is a picothyroid phantom. It's nothing but a monochrome image of radiation of a particular test pattern you are checking. X-ray weld analysis in again in medical fields, and also rainfall levels. For example, in a region, how you can say what are the concentration of rainfall. Some regions have a high rainfall, some regions may have a low rainfall. So again, you test again for that. Okay, this is the diagram for this. F of x comma y is the input image. Again, you are applying individual transform red, green, and blue. Once you get this fr of x comma y for red, gr of x comma y for green and br for x comma y for the blue component. This is the graph for this. Again, it is a sinusoidal wave only. For green, it again starts from here, okay, and again from blue, again a little bit from up from the x-axis, it goes like this. So if you try to slice it off, you see that different intensity levels are trying to, you can say, are catched, because here the graph goes starts from here, again from the blue it mainly starts again near the origin, near this intersection point, again for the blue directly starts with the intersection. That means that different RGB, different components, different intensity levels are sliced off. Okay. Next we have is the image pyramid. Image pyramid, the name only says you have a pyramid shape like structure. Okay, so this method is mainly used to represent images in multiple resolutions. So if a multiple resolution image is there, you are trying to represent that particular image. Okay, now where it is used, it is mainly used in all your machine vision in the sense all the OpenCV and image compression techniques, where images are mainly represented in the form of a hierarchical form. So in hierarchical form only you are trying to represent it. That means what it is saying is, for example, if I consider this as my pyramid, all the lower regions will have all the higher intensity, and once you try to go up, the intensity gradually decreases. That means resolution gradually decreases. So pyramid generally consists of your several levels. Your base level is also known as J, which is of the highest resolution of n cross n. Your top level is 0. Top level 0 in the sense that's lowest resolution of 1 cross 1, and all the intermediate levels which are present. These intermediate levels are mainly present in the form of n by 2 into n by 2. That is a factor of 2. It is reducing it off. Okay. Now size of each level. What is the size of each level is mainly given by 2 to the power j into 2 to the power of j, where j mainly varies from particular range. Total number of pixel at a particular level is given by n square of 1 plus 1 by 4 plus 1 by 4 square plus 1 by 4 to the power of p. Okay. Next is approximation pyramid. Approximation pyramid mainly contains the lower resolution approximation of the original image. Each level is obtained by filtering and downsampling the image. Okay. So there are two types of pyramid. One is approximation, one is prediction. Your approximation pyramid mainly contains all the lower resolution regions of the original image. Okay. Now each level, how you are trying to obtain it, it's mainly obtained by with the help of filtering and downsampling techniques. Whereas your prediction pyramid mainly helps you to calculate the difference between the successive approximation level pyramids. Fine. This is the diagram for that. So again, approximation filter is there, approximation filter, then again an interpolation filter. Again, this is for downsampling, this is for prediction. Okay, once you try to connect this, you get this prediction level interval. So what are the construction of pyramid? What is the algorithm for that? First is you compute a reduced resolution approximation of the level. First, to try to calculate the reduced resolution approximation of the input image. So how you are trying to do it? It's mainly done by using downsampling. Downsampling by filtering the result by a factor of 2. Now what you are doing is, now again place the resulting image at j-1 approximation pyramid. Next is unsampling and interpolation. Unsampling and interpolation, mainly what it will do is it will estimate the image from the lower resolution approximation. Again, you perform unsampling and interpolation. Once it is done, you compute the difference between the predicted image and the actual image by placing it into the residual background. Okay, next is what are the techniques? Techniques like neighborhood averaging, Gaussian law, pass filtering, and subsampling can be used. And next we have is the Laplacian pyramid. How is Laplacian pyramid considered? Laplacian pyramid is mainly constructed by the residuals which are compressed into row intensity arrays. So that's all about image pyramid. Next we have is subband coding. Subband coding is again, it's mainly comes in the under the domain of DSP, digital signal processing, where digital filters are mainly built from unit delays, multipliers and adders and manipulate the discrete signal. Okay. And what is next? It produces output sequence. Now what all output sequences are produced? It is mainly based upon the input as well as whatever the filter is giving the response. So digital filters convolution. First is the how you're trying to calculate the filters output. Whatever filter you see, filters output f cap of n. It is mainly obtained by convolving the input sequence with the filter coefficients. So f cap of n is equal to summation of k equal to infinity to minus infinity h of k into f of n minus k, which can be given by f of n into relationship. First is sign reversal, order reversal, and modulation. So sign reversal is nothing but whatever the filter the result it is producing, you just negate the coefficients. Next is order reversal. Order reversal in the sense like you just reverse the filter coefficient with respect to the horizontal as well as vertical axis. And modulation in the sense you attenuate the sign of the odd indexed coefficients. Preliminaries. So preliminaries mainly deals with the mathematical morphology only. Okay, so mathematical morphology, what it is all about, it's a theoretical framework which is mainly used in image processing where sets represents object in an image. Okay, so what are the sets in morphology? First is the binary image. So what is a binary image? First, a binary image is mainly you can say an objects in a binary image are mainly represented as all sets of white pixels. So these sets belong to a 2D integer space of z square. You can see number 2D of z square where each element is a set of a tuple 2D vector whose coordinates are in the xy coordinate of white pixel in the range. Okay, and grayscale images are mainly represented in the form of z cube where each element mainly contains the pixel coordinates. Then it consists of two components. Each element refers to the coordinates of the pixel and the other refers to discrete intensity values. Okay, and sets in higher dimension spaces can obtain other image of attributes such as color and time varying components. So next we have is the different type of set operation. So mainly key operations, if you see, it mainly involve reflection and translation. So reflection is mainly denoted by b cap. So b cap, you see b cap is given by is equal to w oblique w equal to minus b, which mainly represents the reflection of particular image in a, you can say, particular axis or coordinate in a particular axis or a region, where b is nothing but a set of pixels representing an object. B cap is simply the set of points in b whose xy coordinates has been replaced by the minus or x and y. Okay, suppose this is a particular, if you see it's an image, again it got reflected to this axis like that way. Okay, next is translation. So translation of a set B is mainly given by z equal to z1 comma z2, which is mainly given by this formula bz equal to, here we use term c where b plus z, because we are translating it's not to a particular distance by some vector. Okay, and next is something known as structuring elements. So what is a structuring element? A structuring element in the sense that they are the, you can say, sub images which is used to probe the main image for properties of interest. For example, with this structuring element only, we are trying to find out some properties of the main image. Okay, that is all about SE. And what else is needed? Nothing else. Like when the SE is symmetric and no dot is shown, the assumption is that origin is at the center of symmetry. That means if it is symmetric, so origin will be always at the center. Okay, and next we have is the erosion and dilation. So yes, where it is? Erosion dilation. So what happens here is like erosion, you can say it's a fundamental process in the morphological image processing where you are just removing the noise, simplifying the structure and analyzing the shape of images. Okay, so it's all about removing noise, simplifying structures and analyzing the shape of images. So what are the definition, so what are the, you can say, how you can define it in the same way. For example, we have two terms a and b. Your a is nothing but a set of points of an object or particular object. Okay, and let us suppose think b is a structuring element which is smaller set, which is mainly smaller in size and mainly interacts with a. So erosion of a is mainly given by a, this minus circle of b is equal to z, such that b of z is intersection of a's complement. Okay, so b of z is nothing but, you can say, structuring element of b which is translated by z factor. So by z you are trying to translate it, so b of z is nothing but the structuring element translated by z. So in other words, you can say the erosion operation finds all the positions z when the translated structuring element bz is fully contained within your A. Okay, this is the particular diagram for this. Next, we will shift to dilation. But now, what are the, you can say, some of the applications here? So, application first is mainly, you can say, it helps in noise removal. So, first application is noise removal, shape simplification, boundary extraction. Okay. Next we have is dilation. So what is dilation? Just the opposite of erosion only. Okay. So in dilation, what you do is dilation is an operation, you can say, in your image processing field only, where an image is expanded by another set B, which is nothing but the structuring element. So it mainly grows or thickens the objects in a binary image. So how you are trying to establish the same in the equation is A, this XOR of B equal to z, such that b cap of z summation intersection of A is not equal to phi. That means it states that b of z is nothing but the reflection of B about its origin. Okay, reflecting B about its origin and shifting all these reflection points by z. Dilation of A by B is nothing but the set of all the displacements which is caused, and this symbol is nothing but of intersection only. Okay. And what are the, you can say, characteristics of this? Characteristics mainly helps in expands the object boundaries. Next is what are the applications? You can see your applications include bridging the gaps, because you are thickening the image, so all the gaps will be bridged off. Then you're trying to filling hole fillings and all. Okay, and also feature enhancements. Peace. Next, next topic, next you have is duality. So in duality, what happens is, like duality between erosion and dilation, mainly it is, you can say, dual operations in field of image processing only, where they are connected through set complementation and reflection, where they're connected to set complementation and reflection, where it is like one process continues the next, like first erosion, then after dilation, then erosion again. So this is the equation. For example, A, this minus whole of B complement equal to A's complement X or B cap. Then again, just put the ulta sign of this. Okay, this minus becomes plus, the plus becomes minus. And what are the explanation? And you can see what are the symbols each represent. Where A is nothing but the input image. Okay, B is nothing but the structure. A is the input image. B is structuring element. A of C is nothing but complement. B of B cap is nothing but your reflection which you observe. Your this is nothing but erosion operator. Your plus is your dilation operator. Okay. These are a set of equations which you have to remember. 1, 2, 3. Now, how you are using duality? Duality is again used in your efficient computation. For example, if uh, erosion is difficult to compute directly, then it can be calculated using dilation again. Dilation on the complement of the set. Next, you have a simplification of expression in the sense that it can be easily be transformed using duality to simplify the image processing analysis, and also it helps in processing of symmetric images. Next you have is the opening and closing. Opening and closing is like if we see first about opening, the opening is like remove small objects or protrusions from the background. For example, small dots or regions is that is of no use, you are removing it from the background only. Then next is it what it will do, it will also smoothen the contours and all, like eliminate small holes and fills the gaps. And it also, you can say, it smoothens the contours and breaks thin edges. Okay. And what is the process? First is erosion followed by dilation. Done. This is the equation for this. This is erosion followed by dilation. This is dilation followed by erosion. Closing set. Okay. These are the necessary equations which you have to remember. Now, what is the opening operation? Satisfy all these properties. A opening B is nothing but subset of image. If C is subset of D, then C opening of B is a subset of D opening of B, and A opening B, again opening of B is nothing but A opening B itself. So all these properties you should remember of a morphological image processing. Next you have is the hit and mass transform. So what is hit and mass transform? You can say like first, hit mass transform is mainly used for detecting the specific shapes or binary, you can specific shapes or patterns in a binary image. So what happens, it's mainly achieved by combining erosion properties on both the you can say foreground and the background, identifying the location in the image where a particular structuring element fits exactly. Okay, so in this way, this is all about definition of hit mass transform. Next you have is the how you are trying to apply it. Like first, what you have to do is first you have to set the foreground and the background. Okay, now let us assume like A is a binary image where the shapes are detected. Then there are two structuring elements B1 and B2, where B1 corresponds the, you can say, SC of foreground, and B2 SC of background. Okay, now you are applying one by one operations. That operation, that is a erosion B1 is equal to find. Now what you are doing is you are just doing erosion for the foreground. First you do erosion for foreground, then erosion of background. Okay, first is erosion of foreground. These steps you have to remember: erosion of foreground. Next is erosion of background. Now once you are done, then you take the intersections of both the results. Now third step is intersection process. In intersection, what you are doing is one intersection, two you do, and next whatever the result is nothing but you get the interpretation. Then what are the, you can say, why we are using this hit or mass transform? Hit and mass transform is basically, it is mainly used for your shape recognition, thinning algorithm, then noise filtering. Okay, yeah, that's it. Next we have is some of the basic morphological algorithms, where first is boundary extraction. So what is boundary extraction? Boundary extraction is mainly used to identify the, you can say, edges of an object in a binary image. You have a binary image, you have an object there, you want to try to find out the edges. So boundary B of A, so B of A is nothing but boundary of a particular object of an image of set A is mainly defined by beta of A is equal to A minus A erosion of B. Okay, B is nothing but the structuring element. So basically all these topics will come as define the following or explain what you know about it. Okay, it's nothing as such an in-depth question they'll ask from this topic. So this operation, what happens is it mainly works by eroding the image A and subtracting the eroded result from the original image. Okay, and now the structuring element B can also vary in shape and size depending upon the desired boundary thickness and the nature of objects of A. What are the steps? Steps is erode A using B, and then you compute the differences. That's it. Okay. Yes. Next you have is hole filling. So what is this hole filling? Again, hole filling is mainly used to, you can say, fill a particular background enclosed by a foreground object in a binary image. So a hole is mainly connected region of zeros and surrounded by ones. This you have to remember. Zeros surrounded by ones. Surrounded by border of foreground pixels in this section based on dilation, implementation, and boundary. Yeah, this is the formula. Xk is equal to xk minus 1 erosion of b intersection of a's complement. Okay. So again, A is nothing but the binary image. Your x naught is nothing but the initial marker set. Okay, like the first, if you consider a hole, the first initial marker set of that particular hole from where you want to start. B is this symmetric structuring element, and A of C is nothing but the complement of A. This is nothing but the equation which you have to remember. Your x of k is nothing but dilated result of iteration k. Your XOR, not XOR, the dilation, this is the dilation operator, and the process stops when x of k is equal to x of k minus 1. When it is equal, that means the foreground and the image both becomes, you can say, there is no difference as such. Then you say that yes, the process is completed. Okay, so what are the example, like how will you try to implement it? Like first the input image. Input image is nothing but a binary image with holes, and the output image is nothing but the holes are filled, resulting in solid white regions. Okay, so what are the, you can say, practical applications of this part? Your practical applications mainly include, first is the object recognition, shape analysis, image segmentation. Okay, next we have is extraction of connected components. So what is extraction of connected components? What is the definition of a connected components? Is mainly, you can say, a cluster of cluster of foreground pixels connected based on a specific rule. So what is that rule? How the foreground pixels are connected using 4 connectivity or 8 connectivity. So extracting these components is very useful for analyzing the binary image, and also detecting the object recognition and everything. So what is the algorithm first? Like first is you take the input image which contains all the connected components. Then you take an initial array called x0. X0 array you take. Okay, which should be same size of a, initialized with all the zeros except for a known point, which is except for the known point, which is 1. So if I consider this point is 1, the rest all surrounding will be all 0 0 0 0 0. Okay, now what is the formula for this? Xk is equal to xk minus 1. So this algorithm will mainly terminate here, indicating that all the pixels in all the pixels in the connected component has been identified. So what are the steps? So the first step mainly starts with where you are just choosing a structuring element B. Choose the element B. Then you initialize the x0 array with all the seed points. Then perform dilation and erosion. Next, compute the result. Okay, yeah, that's it. Next you have is something known as convex hull. So again, convex hull has a pretty much, you can say, a theory, not theory as such, a lot of equations only. So convex hull is all about a set of points in a smallest convex shape that contains all the points. In mathematical terms, if you say convex hull is the smallest convex set that contains the original set. Okay, So the procedure mainly starts iteratively by applying all the hit mask transform to the set using multiple structuring elements you are using. So when no particular, you can say, changes occur, the union of all these results are mainly taken to get by the final result. Next is the process typically uses multiple structuring elements which are mainly iterated until and unless you get no further more changes. And that means if a change occurs, you get a matching pattern there. Correct. Then the final result is nothing but the convex hull of the set, which is mainly the final result. So this and this equation is important. You have to write all this. Okay. Next you have thinning. Thinning is mainly used to, you can say, reduce the width of binary objects in an image. So it basically involves iterating through a set using different structuring elements to remove the boundary pixels in a symmetric way. So in a symmetric way, you're removing all the boundary pixels. Next is, you can say, like first is like how you're applying the procedure. Like this thinning operation, this cross, this is B is given by A minus of A star B, again this complement whole you have to give. This thinning can be mainly defined using the hit mask transform, and each thinning is mainly transformed with is performed with the help of a structuring element, and the process continues until there is no changes. A thin result can be converted to M connectivity to remove all the unwanted paths, making sure the connectivity is maintained. Okay. Thickening, again the same opposite of thinning only. The same thing which you are doing is like you are opposite of thinning to increase the thickness of an object in binary image while maintaining the productivity. So this is the equation. Okay, these two. So you can say A is nothing but the input binary image, B is a structuring element which is mainly used for thickening, and the operations involves complementing the set A and applying morphological transforms of set B. Okay. Next you have something known as skeletons. So skeleton is nothing but skeletonization is again one of the, you can say, an operation that simplifies the shape to a skeleton form by retaining the shape's topological properties but reduces the dimension. Okay, the goal is mainly to reduce the foreground object to a very thin, and you are centrally connecting it to the pixels, preserving both the connectivity and structures. So what are the two key components here? First is the maximum disk, and next is skeleton definition. Maximum disk is nothing but the disk at a point of the set is the largest disk centered at that point, and it mainly contains the entire set. So what happens is the disk mainly touches the boundary set at two or more points. So what are the point of skeleton? Point of skeleton is mainly it's a part of the skeleton that it can be the center of a maximum disk that is contained in a particular set. Okay, so mainly you can say to reduce the dimension of a particular object and giving it a skeleton like structure. Very thin you are doing. S of A is nothing but this complete union operation, summation of K is equal to 0 to K, S of K of A. Okay, where B is nothing but a structuring element. K times you are trying to process it, you get this equation. Yes. So what is the skeletonization algorithm? Like first is you first can be computed the following. So first is erosion and openings. So first erode the input image A by structuring element B, then perform openings for the eroded set. Once it is done, you do the perform the union of the difference between the successive erosions and opening, and then reconstruct. Reconstruct in the sense like once the skeleton subsets are computed, the final skeleton can be reconstructed using this formula again. A can be reconstructed from this formula. Okay. Next you have is pruning. So what is pruning? Pruning is an important, you can say, a post-processing step after skeletonization. It is mainly necessary to, you can say, remove unwanted components known as unwanted components or branches that can appear due to irregularities in a particular image. So these components also known as spurs, which mainly tend to distort the skeleton of the character. So pruning is nothing but it arises due to skeletonization. It's the extra edges which comes out. So you have to remove all those things again. So what are the steps? First, you take the structuring elements. It's quite theoretical. So what you do is you first take all the structuring elements that is used to relate the endpoints of a simple 3x3 matrix. You perform the thinning operation. You try to thin the particular image. Okay. Next to do is endpoint detection. Endpoint detection, you determine all the endpoints of a particular object. Then you apply dilation. Dilation in the sense like where you want to expand a particular pixel of a particular image. Then the final image is obtained. So this x1 is equal to a cross of b is equation for pruning. This, this, and this. Yeah, that's it. The next you have is morphological reconstruction. So morphological reconstruction is again a type of, you can say, um, type of algorithm only which you are applying to manipulate and analyze binary images. First is opening by reconstruction. Opening by reconstruction in the sense like first geodesic dilation and operation. So geodesic dilation in the sense like first what you are doing is again you are applying dilation to you are making use of a mask. Okay, so that involves mainly two images. One is the structuring element and one image is the marker image, which mainly contains all the starting points which you want to do the transformation. Other is the mask which mainly constrains transformation. Structuring element is used to define the connectivity. Geodesic dilation is again you can say of size 1 of a marker image is mainly defined by d of g, that is geodesic dilation of one of a particular image. F is mainly given by f dilation of b intersection of g. Okay, now again if you're trying to implement some and or not operation, it will give like this: dg of n of f is equal to dg of 1 n minus 1 into f. So next we have is the morphological reconstructions. Again, it's the same thing only. So what are the some of the sample applications you say? Some of the sample application like first is opening by reconstruction. So opening by reconstruction is mainly a technique where you are trying to restore the shape of objects that mainly uh, after your erosion operation, where you remove all the small objects and everything. And in opening by reconstruction is mainly defined as the, you can say, reconstruction by dilation of the erosion image. So this operation is more accurate than a standard opening because it restores the shape precisely based on the shape of the remaining objects. Okay, next is we have filling the holes and all. Filling holes in the sense used to fill holes in a binary images. The method mainly creates you can say a marker image where only the border of an image, the image border is mainly set to 1 while the remaining you can say is set to 0, and this image is then dilated using a structuring element where you are filling all the holes. Rest also you can have there is something known as automated hole filling where the entire process is automated starting with a complement of an image, creating a wall of zeros around the hole, then dilating the entire image. Next is border clearing. In border clearing, what you are doing is you are just removing objects which are mainly touching the image border. So you are trying to extract the complete object from a particular image for further processing. Okay, for example, the procedure is mainly applied to a text image for removing any object or characters that mainly touch a particular border, and after that you can remove it from them and mainly send it for further analysis. This is nothing but this flowchart is very much important. I would suggest to please remember this. If you remember this flowchart, only half of the job is over because it contains all this formulas how to implement one image processing steps one after the other. So yeah, this is very much important. A double start to this question. With this, it marks the end of module 4. This entire scribbled PDF will be available in the Google Drive link. You can go and check out. Also, I'll try to provide some of the handwritten notes of my own so that it becomes very helpful for the end moment preparation also. So let's see if I get time and make those notes. Till then, please like, share, and subscribe. Important notes and important questions will be uploaded in this playlist very soon. So keep a eye on the channel. Till then, like, share, and subscribe. Wish you all the best for DIP exam.